Hello, everybody. So my initial plan was to go over the last year's midterm today. But then TAs were like, well, the students are going to do this anyway. So typically, we don't like this when teachers do this. So I asked them what they would think is most useful. And they said, why don't you just go over every single lecture for a couple minutes and kind of say what the important points are. Does that sound like a good idea?
I want to finish the Jeopardy.
You want to finish the Jeopardy? The thing is, I posted the solutions to the Jeopardy exam. So one good question is, we could go through the whole class forwards or backwards in time. The idea being is if we run out of time at the end, we either miss the last lectures or the earliest lectures. Any preference? Let's have a vote. Who wants to go through it so the advantage of going in chronological order is that it's easier to kind of say how things build on. There's actually, there was a reason I ordered it that way. On the other hand, if we run out of time, we wouldn't miss the last couple lectures, which may be most relevant, or most, there may be most uncertainty about because we haven't had homeworks and those yet. On the other hand, the others does the reverse. So let's have a little vote. So who wants to go through it in chronological order? Raise your hand. And who wants to go in inverse order? It's a tie. That is tricky. Okay. It's the first time in my life that he actually had a tie. Now I don't know what to do.
The only thing we can do is take a representative from each group and have them do rock, paper, scissors.
What's your question?
Take a rock.
I think the reason you want to go in reverse order is because they're more iffy on the end material. So if we went quickly through the earlier stuff and slow down a little.
Okay, good. Okay, so here's a suggestion. We go through chronological order, but we try to be really fast. So how many minutes do we have? We have 45 minutes. How many lectures do we have? 10, right? Okay, so you have 4.5 minutes. Arthur, you're my time man. So you can, every time, after 4.5 minutes, you can tell me, 4 minutes and 30 seconds. Time me to move on. I try to go through the first ones a little faster, so this way maybe we can save up some time. Okay, please, at every single topic, feel free to ask me questions. So at the beginning, we talked about the general machine learning setup. And sorry, I don't have big chalk today, actually. I apologize. I know somehow someone stole the big chalk. So I have to buy some new ones. Yeah, okay. And the idea, so this whole class about supervised learning. And in the beginning, basically, we just talked about the general framework. A few important things is the data set that we draw, right? We have xi, y1, and so on, up to xn, yn, right? They are drawn from some distribution P, and this distribution, they're drawn IID. Right? So they're all independent from each other, and they're drawn from the same distribution. And the typical goal is to predict y given x. All right? And so in order to evaluate how well we are doing, and to train algorithms, we split the data set D into typically three data sets. We have the training data set, we have the validation data set, and we have the test set. And so the idea is basically you take your training data set, and on your training data set, you train your algorithm. And then on the validation data set, you can estimate what the error is. And the validation data set, because you didn't touch it, that's an estimate of the true error, right? So ultimately, what you care about is the expected error. What's the probability that if I would take a new point from this distribution P, what's the probability that I get it right, right? Or put another way, what's the expected error I would get if I draw a point from this distribution P? And so you can't measure this because you don't have access to distribution P, but you have more data than you need, right? So you take your data set D, you reduce it, you only train on some of it, and then these remaining points, they're basically drawn from this distribution P, right? So we can just use them to evaluate how well your algorithm does. And so on the validation set, you now compute the error. Can anyone tell me why we need validation and test? Yeah? So validation is there to you make sure that you don't overfit over. That's true to the over the training data set. But why do you even need split off one more data set? Yeah. That's right. So typically you evaluate your algorithm on a validation data set, then you realize, darn, right, the error is too high, right? So what do? You try to find a different algorithm, right? Let's say you had the Perceptron, now you get an SVM or something, right? And then you train again, you evaluate, and then you see, oh, that doesn't work, right? Maybe my C was not large enough, right? Let me increase C. So you run it again, test it here, right? And you tweak your hyperparameters until you're satisfied, right? But now you've looked at this data set so many times that this is no longer actually an unbiased estimator of your true test error. So that's why you split up another data set, a little bit of a test data, that you really only touch once, right? So that's the idea. So once you're confident here, this is kind of a sanity check, right? So let's say that you need an error of 1%, right? That's what your boss told you. The first time you run, you get an error of 2%. So that's pretty good, but I have to go get it lower. So now you tweak your parameters, you get an error of 1.5%, right? You tweak your parameters again, change the algorithm a little, add some features to something else, right? Now you get 1.1%, right? And you keep doing until you get 0.8%. That's pretty good. Then you test it on test data set and you get 0.9%. That's probably what the true error is, right? Does that make sense? Okay, so please keep in mind that the validation error basically, these two are basically, are meant to be estimates of the true expected error. And the test error, if your data set is really, really large, is actually, approaches exactly the true expected error that you're trying to minimize, which is also called the generalization error. So the generalization error is the expected error for new data from this distribution. Okay, so that's kind of just the setup, and just make sure you really truly understand how this is done and why this is done. Okay, any more questions about this general setup? Then I move on to Kane and then. Yeah?
If you say training error on the exam, will it be referring to error on the training data set?
Training error is always the error on this data set, after you train. Okay, good. After you train, right? So basically, and typically that's much lower than your testing error. Right? So we know, for example, SVM, right, if the data is linearly separable, it will always find a hyperplane that has zero error, right? But that actually may not be in general the case. Okay, any more questions? Okay, good. So then we went to K-nearest neighbors, right? So K-nearest neighbors is one specific algorithm. And actually, let me just talk about the different types of algorithm that we learned. So we have this distribution P over X and Y. And so ultimately, we want to, given an X, we would like to make a prediction over Y, right? So that's exactly this distribution, P of Y given X, right? So that is, if you have this distribution, then it's easy. Can anyone tell me what you do when you have this distribution? What classifier do you use? Yeah? You use the Bayes optimal classifier, right? So that would be the optimal choice to do once you have P of Y given X. So, one way to do machine learning is try to estimate this probability distribution. And then, but the Bayes optimal classifier does, it just picks the most likely Y for a given X. Another option is to learn a function, f of X, right? Which actually approximates exactly this. So such that this is argmax Y, P of Y given X, right? So basically saying, in this case, I don't learn a distribution. Maybe it's too much work to actually learn a distribution over the label. Really, all I care about is just the one label that's most likely. So a lot of algorithms also just learn a function that basically says, given X, tell me which label is the most likely label, right? So if you have this, of course, you can always get this function. But for example, K-nearest neighbors doesn't actually give you a distribution. It just gives you a function, right? You can make modifications to get a distribution. But typically, it's just this. This is called discriminative learning. There's also generative learning. In generative learning, instead, you learn P of X given Y, and then P of Y. Right? And that's ultimately the same thing. If you have that, then you can just use Bayes' rule and flip it around. Right? Yeah? So they are this, right? They're discriminative. Yeah, that's absolutely discriminative. Absolutely. Yeah, I mean, you never learn what's given a label, what's the probability of a certain x, right? You never learn that at all. Discriminative learning does not mean that you're not doing probabilities, right? You can learn a function that actually gives you the probability of y given x. And you can chain SVM actually very easily into an algorithm that returns you p of y given x. Discriminative says you stick an input x in, and all you learn is the probability of y, right? So think about the following, right? A discriminative algorithm, given all measurements about a human, will tell you, is that human male or female, right? A generative algorithm would tell you, given the gender, generate a human, right? What are the feature representations of a human, right? Well, SVM doesn't do that at all, right? Does that make sense? Yeah? No, Perceptron does this, right? So just, it's a hyperplane. If you're on this side, it's positive, and the other it's negative. But there's no notion of what's for is given y, what's a certain x. Yeah?
Since people seem to be confused between the two, can you go through the algorithms that we've learned so far and categorize the two?
Sure. Why don't we do the following? Why don't we say discriminative, generative, and then we also say parametric, nonparametric. Okay. So let me just quickly talk about parametric versus nonparametric. What's parametric versus nonparametric? An algorithm is parametric if you have a finite number of parameters that you're learning, that you're fitting from your data. So the number of parameters stays the same no matter how much data you have. Can anyone tell me an example of a parametric algorithm? Yeah, Perceptron, right? So you basically have the number, every dimension of W and B. Those are your parameters, right? And then you take your data and you learn these parameters. A non-parametric algorithm is something where there's no fixed number of parameters that you're learning. The model size, how much you're storing, grows with the number of data you have typically. Can anyone tell me an example of a non-parametric algorithm? Yeah. K-nearest neighbors, right? So K-nearest neighbors, you just store the whole data set. And so, the amount of storage that you need grows linearly actually with the data set, right? That's not the case for SVM and Perceptron, right? Where you know up front how big your model is, that's it, right? If you get more data, you're just going to learn a finer model. Sure, okay, so let's just go through them. K-nearest neighbors, where does it sit? Right, so K-nearest neighbors is here, right? What's the next one? Perceptron. Someone else, not Arthur. Parametric discriminative, right? Perceptron. SVM. Naive Bayes. I'm sure someone said it. So generative and parametric, right? Naive Bayes. Did I have them all? Oh, logistic regression. Yeah, where's that? Right, it's same thing here, right? Logistic. And of course, lasso and elastic net and so on. So all these ERM algorithms fit in here. Yeah? Yeah. Now you're getting fancy. Yes, you could do that. That's right. So what he's saying is you could actually do naive Bayes, keep the data around, right? And then actually do non-parametric kernel density estimation or something, density estimation to estimate the probability. Sure, you can do this, but everybody else just forget what I just said. Yes, okay, good. Okay, we have to move on to the next lecture. Okay, good. So, well, this was kind of in between. This is kind of across different lectures. So, then we covered K-nearest neighbors. The K-nearest neighbors is a really, really simple algorithm. You just classify everything, by a majority vote of its nearest neighbors. The key is that K-nearest neighbors relies heavily on the quality of the metric, right? So, one thing you have to remember is what's the assumption of K-nearest neighbors? Similar points have similar labels. The metric has to reflect this assumption, right? If you have a bad metric, such that actually that measures similarity in some way that's actually not compatible with the label, it breaks, right? Or it's not, correlated with the label. And then we went to the one thing you of course have to know is how the proof works with, why does k nearest neighbor, or why does one nearest neighbor, why is the error upper bounded by twice the base optimal error? It's a relatively simple two-step argument. And then there's the curse of dimensionality that basically states, actually, in very high dimensional spaces, the notion of similarity is somewhat, or can be badly defined, right? Can be ill-defined. There are data points, it typically happens that, everything is really far away from everything. And there is no notion of similarity anymore. Or put another way, you would need exponential amount of data to obtain a local similarity. Right? Then, of course, the question is, why does it still work on images and digits? And the answer is because the data is actually not intrinsically high dimensional. Right? It just lies in a high dimensional space. You have a question? Yeah?
Well, my question was, how did you decide if it's intrinsically high dimensional or just high dimensional?
Right. The cheeky answer is if k nearest neighbor still works, it's intrinsically low dimensional. You can test it. So if you basically look at the nearest, so one thing you do is for every single data point, you look at the k nearest neighbors, or for some data points, you look at the k nearest neighbors, and you basically, so there's a bunch of different steps you can do. You could just do local PCA. I don't know if you've seen PCA before. So to actually estimate locally, right, does this lie in a low dimensional space? Globally, it doesn't, right? So, I mean, if you do PCA and you realize globally lies in a low dimensional space, you just have a bad representation. But it could be that locally it's low dimensional. There's also something called the doubling dimension. It basically says, like, as I keep doubling a radius around my point, like, how many more data points do I see in this? So I have a data point. I say, well, within a radius of R, how many points do I have inside this? And now if I double R, right, how many more points do I have? Well, if the data is two-dimensional, right, then it's going to be 4 times as many points. If it's 3-dimensional, it's going to be 8 times as many points, right? So you can actually compute the local dimensionality exactly with this doubling. It's called the doubling dimension. Okay, any more questions? Yeah? Parametric algorithms generally faster, non-parametric algorithms, yes, absolutely. Yeah, that's, there's always exceptions because some fancy stuff, but yes, typically that's the case. Right. Yeah?
So when we say net rate is a parametric algorithm, if we have more trained data, that is when the data grows, don't we have to go back and relearn the probability?
Sure, but the number of parameters that you're learning does not grow. If I make your data set 10 times larger, the final model that you're storing is not any bigger. Okay. Right? For every dimension, or basically just have some description of that the parameters of that distribution for that dimension.
Right, so it's the same number of probabilities.
So the same number of parameters.
Okay. So how is it different in K and N then?
K and N, if I give you more data, you store more data. So the model is the data, right? So you actually have to store more, you need more storage.
So here, the same amount of data is just the value that is changing for nitrates.
That's right. That's exactly right. Okay, good. Perceptron algorithm. So the important thing is, assumption of the perceptron algorithm is that data is linearly separable. Right? If it's not, perceptron algorithm tanks. Right? So you have to understand what happens when it's not linearly separable. It loops forever. Right? And you have to understand the update. What does it do? Right? It looks at one data point at a time, and then if it's positive, it just adds it. If it's misclassified, if it's correctly classified, it doesn't do anything. If it's misclassified, if it's positive, it adds it. If it's negative, it subtracts it. Really simple. Right? It keeps looping over it. The beautiful thing is it converges in a finite number of steps. You have to know how to prove this, right? And what the bound is. The second, little nugget in Perceptron is there's this bias term. How can you get rid of the bias term? We just add one additional dimension, right? And just absorb B in the vector, right? Why is it scale invariant? We talked about this as well, right? So you can just rescale the data set. And that was a little trick to make the proof simpler. It doesn't change anything about the convergence. Any more questions about Perceptron? Otherwise, I move on. That seems pretty easy. Okay, yeah, sorry. Yes, that's what it should be. That was a typo? Yeah, that's the y, right? The y is either +1 or -1. So, yeah. Okay. Okay, so then we talked about, so after the perceptron, we went into, back into this setting and basically said, well, one way to do machine learning is actually just to estimate this distribution, P of x, y, right? So once we had that distribution, we could just use the Bayes optimal classifier, right? And so the first thing we did is we just talked about how do you even estimate, distributions from data, right? So, and so what we talked about is maximum likelihood estimation, MLE, and we talked about MAP, right? So these are the two ways we in this class estimate distributions from data. And so the way it typically works is we assume this distribution P has takes on some specific form, so it could be a binomial, multinomial, etc. distribution, and then that has some parameters, and then we fit these parameters, right? So you basically adjust the parameters of the distribution such that actually it fits what we observed in our data. And what does maximum likelihood estimation do? It basically says what's the maximize the probability of the data given the parameters, right? So these data here are parameters of the distribution, and we say I want to make my parameter such that the data that I observe becomes as likely as possible. Someone posted the questions like, what's the difference between probability and likelihood? And so the way it's used in this class is that likelihood and probability is really the same thing. It's just you can't really say what's the probability of a data set, right? If you have a trained data set, you can't say what's the probability of that data set. It doesn't make any sense, right? Because the data set already exists, right? It doesn't have any probability. It's like asking what's the probability of me? Well, I don't know, right? I'm here. So what you say is it's the likelihood, right, of something that already happens, right? So in hindsight, kind of how likely is it that I've seen that thing that I'm actually seeing? So we distinguish between this by saying either probability of something that hasn't occurred yet and likelihood of an event that has occurred. We just retrospectively analyze the likelihood of that happening. Okay, so MLE just maximizes theta, so it maximizes this given theta, and MAP goes the other way around, this MLE, and MAP says what's the probability, maximizes the probability of theta given the data. Right? So this is what MAP maximizes. And so there's a crucial step here. It's very subtle, but in this case, actually, theta got promoted from just a set of parameters to actually a random variable. So we use Bayes rule to make this P of D given theta times the probability of theta divided by the normalization. This here, the P of D given theta is the same as here. That's why when you do MAP versus MLE, you almost go through the same steps, right? Most of the time. Because you're maximizing this, so you're maximizing this, right? So when you take the logs, that's always the same part plus some stuff on the right, when you do MAP, right? And that plus some stuff almost always turns out to be a regularizer, right? Because it doesn't actually involve the data, it only involves the parameters, right? So you basically get the norm or something over the parameters, right? That's basically where these regularizers come from. Right? That's one way to derive them. Any questions about MAP versus MLE? Then very briefly, we also thought, well, what's the true Bayesian way of doing this? And we didn't really get into the specifics, but you should know roughly what it is. And that's, in some sense, you're basically saying, for a given y, for a given x, what's y? What's the probability of y? And the way this is, can you read this still, or is this too small? Raise your thumbs up. Okay, good. So basically what we're doing here is we say, okay, well, we assume we have some model, but we don't know what that model is. So we integrate out all possible models. We say, what's the probability of y given x and a certain model? And then we say, what's the probability of this model given our data? Right? And so this here is a test point here. This is my test point, test point, test point, test point. And then we integrate out all possible things. So this here, so basically, think about this integral, right? So you basically say, given my data, there's some probability that I end up with a certain parameter set. What MAP does, it just says, what's the most likely one, right? What we're saying here is there's many different choices, and we sum them all up, And each one of these models gives us a different prediction, and we average them out and weigh every one of them by the likelihood of that happening. Right? So in some sense, you basically say, you either compute this integral and say you kind of want to have a weighted average of all models, or in map, you just say, I just take the most likely model and return that answer. Right? So this is kind of the pragmatic Bayesian approach. Ideally, what you want to do as a Bayesian is this, but you typically can't solve this integral. It's very, very hard. So what you do is you just do this map. Right? The way it's often done in practice is you just evaluate this, for maybe a couple thousand values of thetas, and then you average those. It's a sampling approach. Okay, good. Any more questions about MLE map? Bayesian versus frequentist? We can move on. All right, naive Bayes. So now that we know how to estimate probabilities, the idea was, well, can't we just now estimate P of x given y, or P of y given x, right? What is this? Can't we just estimate this from the data, right? So that was the idea, right? Awesome, let's just do this and then we're done, right? We can all go home. The problem is this doesn't work. Can anyone tell me why this doesn't work? What would you need for this to work? If you want to estimate, yeah? You would, yeah, that's right. You would need, basically an infinite amount of data, right? An exponential amount of data to estimate this, right? So, basically what you would do is you would look through your database, look all the x's that match exactly this x, and then say, how often did I observe this particular y, right? So he's right. Right, so every single test point I must have seen during training already, ideally multiple times, such that I can estimate what's the probability for a given label, right? That's completely infeasible. So we can't do this. So what does naive Bayes say? You say, well, we just flip this around. And we say this is P of x given y, P of y, divided by some normalizer. And this doesn't change anything, doesn't make it easier. But this is, now we estimate, this thing we can estimate, that's really easy. We just count how many times do we see each class. That's easy, right? This thing here, let's say how many spam emails, how many not spam emails do we see. This thing here is also hard, but we can make the simplifying assumption that this here factors, right? So P of x given y actually equals, it's conditionally independent. So we can say this is, product over O alpha, P of x alpha given y. Right? Doesn't have to be exactly this. Actually, it can also just be a function, to be honest. It just doesn't have to be well-defined probabilities. So actually, in the multinomial distribution, these are actually, if you're very, very careful, you realize they don't actually normalize. So it's just functions. But it doesn't really matter. Like if you just say these are conditionally independent, that's exactly, everybody understands what you mean. That's correct. Any questions about naive Bayes? Yeah?
So the assumption usually gives like valid data, even though, or valid predictions, even though it's not right for many data sets. Is there any intuition on why it generally works? Or is it just we found out in theory?
Is there any, yeah, okay. So the question is, I mentioned multiple times in lecture that this is typically not true, right? And that's correct. So why does it still work in practice? And the assumption is, well, basically it's not true, but it's not totally off, right? So if your distribution is okay, right, then, or it may not matter all that much, right? For emails, for example, the word order doesn't really matter, right? So that's maybe why it's most wrong, right? It ultimately turns out you can easily detect if something is spam, like even if the email was written backwards in any particular order. I think that's the best I can give you, basically, right? But that basically is an overly strict assumption. Yeah. Good question. Yeah.
Is there a data set where it breaks down like really correlated digital error?
Oh, well, so there's two things, right? So the first assumption you're making is this. The second assumption now is, what are these factors, right? And typically, we say these are now independent probabilities for each different dimension. So each dimension now is basically, we can now estimate that individually. And now we make the second assumption. We're saying, well, what is that distribution, right? We, for example, say that's my multinomial Gaussian or something. Typically, that's where it really breaks down, right? So if you assume a Gaussian distribution, but they're not Gaussian distributed, right, then horrible things will happen, right? And this is exactly, someone actually posted that question on Piazza, right? If we have data points like this, and so let's say we have one more cross here, right? What does naive Bayes do, right? So naive Bayes now looks at each dimension individually. So this two-dimensional thing, that doesn't matter for naive Bayes. Just looks at the first dimension, so projects everything down here. Right? So these are all the points basically projected down. So I just collapse it, just project them onto this x-axis. And then I fit a, let's say I'm assuming Gaussian distribution, I fit a Gaussian around the circles, I fit a Gaussian around x, right? And now comes the crucial part. I'm not, once I have these Gaussian fitted, I don't look at the data ever again. I just use the data to estimate the parameters of my distributions. So now I do this on the other side as well. So here I actually have actually I get these distributions here, right? And what it will do, it will actually find a hyperplane to basically separate these two distributions, which will look something like this if you put them back together, and it will find a hyperplane here, right? So despite that it is linearly separable, it will actually not separate this point correctly, because once I estimated the distribution, that guy was such an outlier, basically, like based on these distributions, the best hyperplane is still here, right? And so that's typically where things fall apart, right? So if your data set actually is not Gaussian distributed, or not monomial or something, that's a bad estimate, then you will get very different distribution than your data, and then actually your classifier will just do the wrong thing, right? And a good test could be if you actually take these distributions and you sample points from it. Do you get stuff that looks like your data, right? If your assumption is right, then you will get something that looks exactly like your data, right? And if you now get points, so in this case you would get points here, 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 but you would never get that point, right? That's really, really unlikely, right? So that's kind of where things fall apart, right? So apparently in your data set you actually have a little bit of probability mass here as well. Someone asked, when does logistic regression and naive Bayes get the same result, right? And that's basically logistic regression, and that's the next lecture now, says, okay, instead of actually estimating this, we estimate this, right? But use the same form for this that we actually get from naive Bayes, right? Which is, this is 1 over 1 plus e to the minus y w transpose x. So this is my w in this case. W and theta is the same thing, right? So logistic regression fits the points. Naive Bayes logistic regression separates the data points. Naive Bayes separates the distributions which it fit on the data. That's the crucial difference, right? Those two give the same result if your data distribution actually fits your data, right? Because then it's the same thing, right? If the data is actually drawn from these two distributions, then it doesn't matter if I'm separating the distributions or if I'm separating data points drawn from this distribution. That's the same thing, as long as n becomes large enough, right? So asymptotically, as n becomes very large, if the data assumption holds, that means the naive Bayes assumption holds, and my modeling assumption for distributions hold, those two algorithms are identical, right? Often they are not, and therefore, logistic regression actually, tends to work a little better. Yeah.
Ever a case where naive Bayes is better than logistic regression?
Yes, good question. So is there ever a case where naive Bayes is better than logistic regression? The answer is yes. And typically it's when you have very little amount of data. If you have very little amount of data, then actually logistic regression can easily overfit to the few data points you have, right? But so you basically have some distribution here, but you only have very few points drawn from it, right? So it's really not clear what this distribution looks like. So what naive Bayes does is if you actually, by giving the distribution a very specific form, by saying it is Gaussian, for example, right? Or by saying it's multinomial or something like this, right? You are introducing additional structure into the problem. And if you're right about this, then you're helping the learning algorithm converge better, give better decision boundaries, right? So if you have very little data, that additional knowledge will help you, right? And you will get a better classifier. If you have a lot of data, it will hurt you, right? Because if you have a lot of data, Now what you're doing is you're saying this has to be a Gaussian form. But if you've sampled 1 million data points from this, right, there's no point in, why do you have to restrict it to be a perfect Gaussian, right? You can just let the data speak for itself, right? So that's the advantage of the logistic regression. So typically when you have a lot of data, logistic regression does better. If you have very little data, it's typically advised to use naive Bayes. Yeah?
If your assumptions about the Gaussian points of the teacher's standard deviations aren't independent of class, are the naive Bayes and the logistic regression still the same?
No, then they become different. Yeah. Because this is no longer this is no longer what naive Bayes models. Yeah. Yeah. Why would you ever use logistic regression? The question is, why would you ever use logistic regression over SVM? One thing that's really nice about logistic regression is it gives you well-defined probabilities, whereas SVM doesn't. SVM just gives you a prediction, right? Which way on the hyperplane you lie on. Some people combine both. So SVMs sometimes give you slightly better prediction performance than logistic regression. And so what people do is they take the output of SVMs. It's just one feature, right? Like this is the prediction of the SVM. Not where you lie on, but the W transpose X plus B from the SVM. That's one dimension for every feature, for every data point. And they stick that into a logistic regression classifier. And train one more time. Then you also get well-defined probabilities for SVMs. And that idea is actually called Platt scaling. So it was invented by John Platt, and it's become very famous, actually. So it's a famous algorithm. Yeah, good point.
So with the mixed number distribution, we can still express like the naive Bayes of this format.
Sorry, say it again?
Like with the mixed number distribution, we can still express the naive.
Yeah, multinomial also, that's right. So also
So like does the logistic regression make the assumption that it is normal distributed, or it doesn't make any assumption?
it makes assumption it's actually from an exponential family. Yeah. So it could be multinomial or Gaussian, right? And by using naive Bayes, you actually make that specific. So you're putting in more information, which helps you if there's very little data, if you're right. That's basically what it is. But that's also why logistic regression is more flexible if you see a lot of data. Yeah? Why does it give well-defined probabilities? Because that's what you're estimating, right? You're estimating P of Y of X, W. So you're basically, you're maximizing the likelihood of your data. So SVM, there's no probability at all, right? At the end, you're either on the right side, the positive side, or you're on the negative side. There's no probability at all. So the downside of an SVM is it's hard to read certainties from this, right? It just tells you this is class 1, this is class minus 1, but you can't really tell if it's really sure about this or if it's not really sure about this. So if you have a self-driving car, it tells you this is a pedestrian, right? You don't know how sure it is about this, right? Or this is not a pedestrian, right? Or maybe it's 49% sure it's, 51% sure it's not a pedestrian, right? You may still want to slam on the brakes not to run that person over, right? So that's why these probabilities are important for decision making. Yeah?
Can you not estimate that based on the distance of the point from the hyperplane?
You can, but actually that's not part of the optimization problem. There's nothing in the optimization problem that tells you that points that are really far away. I mean, because it's scale free, if you have two different SVMs, say, right? And you compare them, it makes no sense to compare them, basically, right? Because the scale is just conveniently set such that the optimization problem becomes easy. Not that it's interpretable. Yeah, any other questions? All right, okay, good. We've got logistic regression, yeah?
Does logistic regression work for non-exponential distributions?
So it works surprisingly well on all kind of data. Right, so if it's just, it basically finds a linear decision boundary, right? So if you just look at it in the ERM format, it's just another way of defining a loss function. Yeah. Okay. So logistic regression, basically we minimize this directly, and then we realized one thing, right? We realized if we define this, we actually, if we put in the MLE, we get a function that we want to minimize, but there was no closed form. So this was we took a little detour for a couple of lectures, basically say, if you get a function, how do you minimize that function, right? So in this case, there's a few things I told you about this function. A, it's differentiable, it is continuous, and it's convex. So that's nice. So that means we can do local hill climbing, right? So the function looks something like this, some salad bowl shaped thing. It doesn't have to be symmetric. And so if we want to find the minimum, that's the maximum likelihood estimate for logistic regression. And so we talked about a few little algorithms how to optimize this. So you start with some point. Typically you say W is all 0, but it doesn't matter. It can be anything you want. And then basically what we do is we say, well, we have the form of this function. We just don't know where its minimum is. So what we do is we do a Taylor expansion. And so Taylor expansion either becomes linear. So if it's linear, then it's really easy to figure out which way to go to reduce it. And as long as your step size is small, you can actually, this approximation is not bad. So you take a small step, and then you end up here, and now you again estimate with a linear function. You take another step, and now again you estimate it, right? And you basically, every single time, you just take the gradient and go in that direction. That's gradient descent. Newton's method goes a little more aggressive. What it does, it fits a parabola on this, it says the quadratic, so basically takes a second order Taylor expansion, finds the minimum of this, jumps to it, and it does this repeatedly. The downside of Newton method is, so the upside of Newton method is it converges very quickly. Few steps and you converge, maybe 10 steps. The downside of Newton's method is that there's no guarantee that you're converging, right? Because these steps can be pretty large. And so that's the problem. With the gradient descent, you can force your steps to be really, really tiny. With Newton's method, the nice thing is these steps are very fast. That's the good. The steps are really large. So in a few steps, you're at the minimum. But it can also be that you're actually unlucky, right? And the parabola you're fitting looks something like this. And the minimum is over here. And then at this point, your function is really, really large. And so now you're diverging very, very quickly, right? The second downside of Newton's method is that you have to compute the Hessian, which is a d by d matrix, and can take up a lot of memory and can be very, very hard to compute, expensive to compute, and then you also have to invert it. So inverting a d by d matrix is order d cubed, so that can be very slow. Yeah?
If you use the heuristic that if your value increases after you form a Taylor series, and if it is, you go back and you decrease the size of the increment, you still not converge.
Sorry, explain that one more time. If you
When you have the, when you find the Taylor expansion,
yeah
and for Newton's method,
yeah
if you find that you basically go to a point that is divergent,
yeah.
can you test that and then basically?
So you can test this, and then you can go back to gradient descent. That's what people typically do. So they do a first order Taylor expansion, so gradient descent, until they get bored. Then they do Newton's method. And if that works out, it's great. And if they diverge, then they just undo this and go back to where they started Newton's methods. They've saved that vector beforehand, and just keep doing gradient descent and just try this again a couple of times. And so occasionally just do a step at, am I ready to do Newton's method? Yes, great, right? No, all right, never mind. Let's wait a few more steps. Make sense? Okay, so yeah. So when it converges, it can be way faster. Way, 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 way faster. So if your data is not very high dimensional, the question that could be a typical exam question. When do you want to use one and when do you want to use the other, right? So if your data is not too high dimensional, right? If it's a 15-dimensional data, well, a 15 by 15 matrix is nothing. It takes a couple of milliseconds to compute or invert, right? No problem at all, right? And now you're done in a few steps, right? But you might have many, many data points. So computing the gradient every single time. Let's say you have 100 million data points, right? But they're only 15-dimensional. Computing the gradient takes a long time, right? In comparison, computing the Hessian, right? I mean, it takes the same amount of time. You go over the data set, right? But then inverting the Hessian is nothing, right? And so if you just do 10 steps of Hessian inversion, that's nothing compared to taking maybe 5,000 gradient steps, right? You have to go over your data set 5,000 times. So, okay, then we also talked about autograd. So don't forget autograd. So one thing about gradient descent is that you have to have the step size, and One thing that AutoGrad does is basically sets a different step size for every single dimension. And it sets it automatically. It's very neat that way. I guess you all did it for your homework, so I guess you know it pretty well at this point. Yeah? Other cases, yeah, of course. If D is very, very large, you know, if D is larger than N or something, right? So then actually you get some non-invertible matrix. Yeah, that can also be the case. That's right. So if Hessian, that's another reason not to use Hessian, and not to use Newton's method. One thing you can do, you can approximate Newton's method by just computing the diagonal of the Hessian. And that's easy to invert, right? And that's very easy to compute, it doesn't take much memory. So that's a very common trick. But that's then similar than AutoGrad, where you actually basically have a different step size for every single dimension. All right, then we did linear regression. So linear regression, in some sense, continues everything that we've done. We have data. And we try to find a line that best explains the data. We just said the noise here is Gaussian. So then the moment we have this Gaussian noise, we can actually use our framework MLE or map. And what we get is just the square loss if you use MLE. Or we get square loss with L2 regularizer when we use map. So it's very simple. And then in some sense then, all right, so now I did run out of time, the last couple of things. So SVM, any questions about SVMs? So SVMs, SVMs say, how do you want to find the maximum margin hyperplane? And one thing we showed is that basically, if we do a little bit of math, then it turns out the margin here becomes exactly 1 over W over the norm of W. So what we can do is we can just maximize the norm of minimize the norm of W. This way we maximize this term here, and so we maximize the margin, right? So the SVM then says maximize the norm of W, and then subject to the constraint at all the points on the right side of hyperplane and exactly 1 off. So make sure you know how to derive this constraint, right? It's just a few lines of derivation. Yeah?
With SVM with soft constraints, with ordinary SVM we rescale the margin to be 1 to solve this.
Yeah?
SVM with soft constraints, does the 1 still have the same meaning in that it's like rescaling the minimum margin?
Yeah, so no, because then actually some points move in here, right? And so you basically say, these are basically absorbed by the slack. So you're basically saying the margin minus the slack is 1. Right, so this here basically would then have some value here on this psi I, which you assign, right? So you're basically saying now we have a soft margin. The margin basically is the distance to the point, minus the amount of slack that I allow this point to actually get inside the margin. That's the definition. Does that make sense? Okay, good. And then yeah. Why can we not absorb the B into the W vector? Very simple. Because we have the constraint here, yi W transpose xi plus B is greater or equal 1, right? So here we could just absorb the B into W, right? Wouldn't make any difference, right? We just have one more dimension, we have one more dimension here. Here it would be a problem, right? Because what you're doing here, what is this? This here is, we actually maximize the square. This here is the sum over all W alpha squared, right? If you now absorb the B in there, you're changing just the definition here, but then you're also adding a term B squared here, which is a different optimization problem.
Right, but in the logistic regression, we do that, and in the L2 regression of the logistic regression, we also have the W transpose W. So, wouldn't that?
Yeah, so here, okay, good. You got me. So typically when you use logistic regression, you use it on very high dimensional data. Often you don't even need a B. So you just drop it. People just drop it. Yeah, that's basically the short version of it. Right? With an SVM, the nice thing about SVM is this very nice definition of finding the maximum margin hyperplane. That's what they are, trying to do, and that's what this doesn't do anymore. But you're right. With logistic regression, the kosher way of doing it is also not to do this. But when you use regularization, right? The moment you do regularization, you have to be careful that you don't regularize your B. Yeah.
In homework 3, I think the equation for SVM did not have to be there. Did we just stop it?
This was to save paper. Okay, it may have been a mistake, yeah. So typically there's a B in it, yeah. Okay. Shall we stop? I guess we have 4 minutes over, right? Okay, good luck, everybody. Eat fruit and look through the notes and look through the past exams.